In this video, we're going to look at exponents, exponential functions, and different exponent rules. So if we start with an example of x to the third times x to the fourth, comes out to be x to the seventh. Why is that? Well, when we have a base that's the exact same, so in this case we have two x's, they're the exact same, and they're raised to a certain power, when we're multiplying these two terms, we end up adding these powers. So a general formula can be a to the m times a to the n equals a to the m plus n. This means that a is going to be the same number, the same variable, just the exact same base. And then m and n are going to be two different exponents that a is raised to. When we have this exact scenario, we're going to keep our base. We're not going to add them. We're not going to multiply. It's going to remain what it is on the left side. And the only difference is that our exponent is now going to be the sum of those two exponents, m and n. So let's look at another similar one. If we have y to the second power times y to the fifth power, what will we get here? We will get y to the seventh power. That's because we have the same base here, which is y. We're going to have the same base here at the end, y. We're multiplying them, so we know all we're going to do is just add those two exponents together. So we do 2 plus 5, that's how we get our 7. If we look at another one, this time with numbers, if we have 3 to the first power times 3 to the second power, what do you think we'll get here? It'll be 3 to the third power. Let's check again. Our bases are exactly the same. So in our answer, we're going to have the same base. We're multiplying them. So now we know we're just going to add those two exponents together. We do 1 plus 2 to get our 3. Let's look at an example with coefficients. If we have 2x squared times 5x to the third, what will our answer be here? You may think that we can't do this because we don't have the same base, but we actually do. The base is the number that has the exponent associated with it. So it's the number that's being raised to a certain power. If we look at 2x squared, that second power is only referring to the x. It's not talking about the 2. If it were, we would see it shown like this, with the 2x in parentheses to show that they're combined, that they're together, and as a whole that term is being raised to the second power. But we don't see that. We only see that second power going with the x, not with the 2. So our base for the first term is just an x. We see something similar in the second term, 5x to the third power. That third power has nothing to do with the 5. It's only talking about raising the x to the third power. So our base for both of these is still going to be an x. So we can either work with our base first or with our coefficients because it's relatively easier. So if we look at the coefficients, it's just going to be 2 times 5. We're going to completely disregard the base and the exponents because we're going to work with that later. So this is just simple multiplication. If you take out the base and the exponent, you just have 2 times 5. So the first part of our answer is going to be a 10. Now let's look at our exponents. We have an x squared and an x to the third. That's the same base. We're multiplying them together, so we know we're going to add our exponents. We're going to keep our same base, and then we're going to do 2 plus 3, which gives us 5. So our final answer is 10x to the fifth power. Let's look at a different example. If we have x to the sixth divided by x to the second power, what will we get here? Well, we're not doing multiplication anymore. We have a fraction which indicates that we're going to do division. So in this case, we still have our same base. We still have an x on the top and x on the bottom. Just how with multiplication, we ended up keeping the base and adding the exponents together, we're going to do the opposite here because division's opposite of multiplication. So if we have x to the sixth divided by x to the second, we're going to keep our same base, but instead of adding our exponents together, we're just going to subtract them from each other. So we're just going to do 6 minus 2 and get 4. So our answer here is going to be x to the fourth power. let's look at a general formula for this. So we'll have a to the m divided by a to the n. That's going to give us a to the m minus n. So if we take a look at this using the same variables as the product rule example, we're going to have our same base, our a. The top one's raised to the m power, whatever number that is. The bottom is raised to the n power, whatever number that is. We're going to keep the same base in our answer, and we're just going to do m minus n. This is the general rule for the quotient rule. So quotient rule is when we have the same base and we are dividing them, and we essentially are just going to subtract those exponents just like we looked. So let's do a couple follow-up examples of this. If we have y to the fifth over y to the first, what will our answer be? Well, if we look at our bases, the number that's being raised to a power, it's the exact same. We have y on the top, y on the bottom. So we know we can do the quotient rule here. So all we're going to do is keep our base, and then we're just going to do 5 minus 1. We're just going to subtract our two exponents, and we're going to get y to the fourth power as our answer. Let's look at one with numerical values. If we have 8 to the fourth power divided by 8 to the second power, now you can do 8 to the fourth power and then divide that by 8 to the second power, and you'll get the exact same answer. But it's so much easier to just use the quotient rule here. We have a base of 8 on the top and a base of 8 on the bottom. So we can apply the quotient rule here. So we're going to keep our base of 8, and then we're going to look at our exponents. 4 minus 2, it's going to be 8 squared, or 64. Now let's combine these two. If we have something like 12x to the 7th divided by 3x squared, let's see what that'll equal to. Remember, just like we did with the product rule, the base is just the number that's being raised to the power. So in the top, in the numerator, the only thing that's being raised to the 7th power is the x, not the 12th. And in the bottom, the only thing that's being raised to the second power is the x, not the 3. So we have the same base here of x. So first we're going to look at our coefficients, and we're just going to solve them like normal. 12 divided by 3. That's going to give us 4. Now let's apply our quotient rule. We have the same base of x, so we can put an x. And since we're dividing them, we're actually going to subtract these numbers. So we're going to do 7 minus 2, giving us 5. So our final answer here is 4x to the 5th. Let's look at another rule. This one is the power of a power rule. If we have x to the second power and we raise it to the third power, what will our answer be? So like I said, this is power of a power. We have a power, x to the second power, and we're raising that to another power. We're raising x to the second power to the third power. So when we're raising it to a power, that's when we'll multiply those exponents. So it might be a little confusing. The product rule, when we're multiplying two things with exponents in them, we're going to add them. But when we're raising a power to another power, that's when we're actually multiplying. So we're going to keep our base here of x, and then we're going to multiply our exponents together. So 2 times 3 giving us 6. Again, let's look at a general formula here. If we have a to the m power, and all of this is raised to the n power, our answer is a to the m times n, which is just like we saw here. Let's look at another example here. If we have y to the fourth power, and this all gets raised to the second power, our answer will be y, and then we multiply our exponents together. 4 times 2, giving us y to the 8th power. Let's look at one with coefficients in them. If we have 2x to the third, all raised to the second power, let's look at what our answer will be. So the power of a power rule only applies when we have an exponent. So this 2 coefficient is not affected with this 3 that's down there. Because like we saw in other examples, we would have seen it as 2x to the third power like this. Now the 3 has an effect on that coefficient of 2. But we don't have that. We just have a coefficient of 2. So this 2 is just going to be squared like normally, giving us 4. Now, we have x to the third, a power, and this is being raised to the second power. So this is where we apply our power of a power rule. So we're going to do x, we're going to keep our base, and then we're going to do 3 times 2, which gives us 6. Let's look at one more of these. If we have 5x squared, and that's raised to the third power, what will our answer be here? Well, as we can see by the coefficient, there's no power, that second power, there's no power on it, so we're not going to do power of a power. We're just going to cube it as we normally would, as if we saw 5 to the third power. So this will give us 125, and now we can do our power of a power, because we have our x squared, our x is raised to a power, and that is raised to the third power. So we're going to keep our base of x, and then we're going to do 2 times 3, which gives us our 6, with a final answer of 125 x to the 6th power. Now we mentioned this a couple times in our other power rules, but now let's look at the power of a product, what that actually means. So in the other examples, I mentioned using something like 3x in parentheses raised to the second power, let's say. What this means is that the 3 and the x are both being raised to the second power. That's why they're in parentheses, to show us that they're in a group together, and that second power is affecting that entire group, everything in those parentheses. So this would look like 9x squared. We're going to square this, and then we're going to square this. So a general formula for this would be if we have ab to the n power, we can rewrite it as a to the n power plus b to the n power. And this is the power of a product rule. We're multiplying these two terms together, the 3 and the x, and the power is going to the product of that, 3 times x. So let's look at another one just to clarify. If we have 5y all raised to the third power, similar example that we saw before, we can rewrite it as 5 to the third power plus, so let's look at a general formula for this. If we have a times b in parentheses raised to the n power, we can rewrite it as a to the n power times b to the n power. So we essentially just distribute that n charge to all the terms in the parentheses that it's affecting. And again, this is the power of a product. So let's look at another example. If we have 5y all raised to the third power, we can rewrite it as 5 to the third power times y to the third power, which further simplifies to 125y to the third power. So we're essentially just going to distribute that charge to everything in the parentheses that it's affecting. Now let's look at a trickier one. If we have negative 2x all raised to the second power, what is our answer? So we're going to distribute the charge, that second power, to the negative 2. So we'll say negative 2 squared, and I'm going to put the negative 2 in parentheses so I know to include the negative when I calculate. And then we can multiply this by x squared. Well, what's negative 2 squared? Negative 2 times negative 2, the negatives cancel out, and we'll just get 4 times x squared as our final answer. Now, another rule that's much simpler than the ones that we've already looked at is the zero rule, or the zero exponent rule, which is essentially anything raised to the 0 power equals 1. So if we have a to the 0 power, it's going to give us 1. And a can be any variable, any coefficient with a variable, any just numerical value. It's just going to equal 1. The only thing that a cannot equal is the number 0. So we can say a cannot equal 0, because this won't give us a real number. So if we have 5 to the 0 power, we'll get 1. If we have negative 3x raised to the 0 power, it's still 1. So anything raised to the 0 power is just going to give us 1. Now let's look at negative exponents. So if we have x to the negative third power, you'll see it rewritten as 1 over x to the third power. So let's talk about this. If we have a variable, a number a, and we raise it to the negative n power, what it does is a negative exponent essentially means to flip the number over. So we can think of this being over 1. We would flip this fraction and have it be 1 over a to the n. What this does is it makes the negative exponent into a positive. So just to reiterate, we start with a negative exponent. We're going to flip this fraction with that imaginary 1 on the bottom, so it's 1 over our original number, with the only difference being that our exponent is now going to be positive instead of negative. So if we have y to the negative first power, we can rewrite it as 1 over y to the first power. So like I said, all we're doing is flipping the fraction, and then we're going to have our exponent be positive. So that means if we have y over x, and all of this is raised to the negative first power, we're going to just flip the fraction. So then it's going to be x over y to the first power, which is the exact same thing. And it also works the other way around. If we have 1 over x to the negative second power, that is the same as x to the positive second power, because what we did here is we flipped our fraction and just made the exponent positive. Let's do an example of this while also trying to combine some rules. If we have x to the negative second, y to the third over y to the negative first, how can we simplify this? Well, what we want to do to simplify is have all of our exponents be positive and only have one of each. We have two y's, a y to the third and a y to the negative first. To simplify, we want them to be positive and only have one y somewhere. So what we should start by doing is flipping all of the terms that need to be positive. So we can keep the y to the third here, and then we'll bring the y to the negative first power, we'll bring that up, and essentially flip it with the x to the negative second and make it x to the second. So we wouldn't flip the entire fraction, because we can say that this original fraction is like x to the negative second over 1 times 1 over y to the negative 1 times y to the third over 1. So even though they're all together, we can break this up into 3 separate fractions and flip them like that. That's why we're not just bringing y to the negative first to the top, and then we have to bring the whole top to the bottom. Since they're multiplied together, we can break them up into individual fractions and flip them like that. So then we only have to flip the x to the negative second since we have to. We can flip the y to the negative first because we have to. But we shouldn't have to flip the y to the third because that's already positive. And this is why. So now we have y to the third times y to the first over x to the second. So now we can use our product rule on the top. Since these two are being multiplied together, we can just add those exponents. So we'll have a y to the fourth over x to the second as our final answer. Now, just to mention it a little bit, we can talk about exponential functions. So if we have something like y equals 2 raised to the x power, this is a function. We have a y, we have an x. This is going to be an exponential function. So that means we're either going to grow or decay exponentially. Now there will be a whole nother video to go over this topic, but just real quick, the way we would want to graph this, or even get some values for this, is to essentially make a table. So if I set up a table of x values and y values, I want to stay around my origin for this just to make it easier. So I can say my y values, so I can say my x values are -2, -1, 0, 1, and 2. And then we can plug each one in to our function here, our equation, and see what we get for y. So if we do 2 to the negative second let's write this out, 2 to the negative second. This is a negative exponent. We know to flip it with our negative exponent rule. It'll be 1 over 2 to the second. 2 to the second is 4. So this is like 1/4. So we could put 1/4 here for y. The next one's negative 1. So we'll do 2 to the negative first power. And we can flip this to 1 over 2 to the first power, which is just 1 over 2. So we could put 1/2 here. 0. Now we have our 0 rule. We're going to have 2 to the x power. 2 to the 0 power. And what does that give us? 1. And now we just do our exponents like normal. 2 to the first power, which is 2. 2 to the second power, which is 4. So this is going to be exponential growth. As you can see, the further we go down, if we plug in 3, we're going to get 8. This isn't linear, it's exponential. So if we were to see what this would kind of look like, it would end up going like this. The more we're going to the right in the x direction, the faster and higher we're going to go. And the more we go to the left, the closer we'll get to 0, even though we'll never get to 0.